Thank you very much, Mervyn. Perfect. Okay, so welcome to the Ulster University Centre for Sustainable Technologies Solar Laboratory. As Anka alluded to, Botswana has a very high level of solar radiation, but conversely here in Belfast we have a very low level of solar radiation, which makes us an ideal place for being a solar laboratory. Because basically, if we can make solar work here in Belfast, we can make it work pretty much anywhere in the world. And this does have a bit of a challenge for us on a day-to-day basis, that we don't have a lot of sun here in order to test equipment. So we've developed a number of years ago a solar simulator facility, which allows us to have a controlled solar environment, controlled temperatures to test pretty much anything under the sun, as we like to say. We can test solar PV panels, we can test solar thermal panels. We've even tested things like ice cream freezers as well. So anything that is exposed to the sun can be tested here in our laboratory. And I will just turn my camera around and walk you through our current tests, which are on the SwanaSmartStore system. There we go. So this is our solar simulator. It's an array of very high-powered lights that you can see at the top there, and this large glass sheet in front of them controls the temperature of the elements that are underneath the light and protects them from radiation. And you can see underneath our SwanaSmartStore system, this is the single module unit, the entry-level system that Mervyn was talking about there before. There's a 60-cell photovoltaic panel there, the large blue panel on the right, and on the left is the solar catcher 28-litre water tank. So these are the sort of core energy collecting elements, obviously exposed under our simulated solar radiation here in the laboratory. Now the power from the PV runs along cables along the ground here into what I'm going to call the SwanaSmartStore brain, effectively. So this is where we harness the electricity and we decide what happens to that electricity. So it all comes into this element here, which is a solar charge controller. And from there, the SwanaSmartStore controller decides where that power goes. So by default, it goes into the battery storage, which are two large lead acid batteries that we've got under here. That will actually be a lithium ion battery in the actual real system that we'd implement, but for laboratory purposes, they work particularly well. And once the power's in the batteries, we can really choose what we do with that. Now, one of the key things that SwanaSmartStore will do is support a domestic load in a house. Now, to simulate that in the laboratory, we have an array of small lights, which are controlled by timers. So these are timer switches here. We have 6 different channels of timers. What we can do by switching the lights on and off in a particular sequence is to simulate a domestic power load. So somebody switching on and off lights in a house, people switching on and off televisions and other appliances in the house. So that's set on a timer sequence to simulate an occupied household. So that's effectively our base load for electricity. Now, Mervyn also mentioned that what SwanaSmartStore does is provide us with hot water. We talked before about the solar catcher unit. So this is the unit under test. We've got cold water coming in via a hose pipe into the unit. That maintains the unit full of water. And I'm just going to walk around. At the other end of the solar catcher is the outlet side, which we've basically got modelled. This would obviously be connected to the domestic plumbing in a house, but at the moment it is essentially just a feed into a water container, which allows us to measure quantities of water and flow rates. And at this end of the solar catcher, we also have the immersion heater. So these cables here, you can see with my hands on, they provide power to immersion heaters, which you may be able to see just in there. It's a little bit dark. They provide extra power into the solar water heater to provide top up energy for days when we don't have enough solar energy. And one of the things we've been investigating in the laboratory are different operating scenarios for immersion heaters. So one of them is to make sure we maximize all of the electricity that's produced by the PV. So imagine the PV panel is producing electricity. It's a nice, bright, sunny day. The battery itself is full because it's fully charged, and we don't have much happening in the house in terms of loads. That means that we're essentially going to have surplus electricity produced by that panel that we don't really want to waste it. So what we do is we dump that surplus in the form of heat into the solar catcher tank to maximize the amount of hot water that we've got. Now, conversely, on a cloudy day, we may not have quite enough sun to provide as much hot water as we want. And on that day, we have a scenario which we call auto top-up, which is essentially an immersion heater taking power from the battery just to maintain a minimum basic level of temperature in that tank so that somebody can have hot water available at pretty much any time. And Mervyn mentioned also the Masood switch, which we've labeled as the Masood switch here, which is essentially a higher power immersion heater which can provide a boost of extra power. For instance, if somebody was about to have a shower in the morning when the tank perhaps isn't as hot as it ought to be, we can give that an immediate boost to provide some extra hot water. Now, SwanaSmartStore can be used in two main configurations. One is as a standalone unit, which is essentially similar to what we have in front of us here, where the only water heating in the household is actually from the solar catcher. So it's a pure solar-only system. That's suitable, we feel, for lower income households where perhaps currently they would only have a cold water supply and are currently boiling pots and kettles to get that hot water. But in the higher income scenario where we have, a house with full modern appliances, they've already probably got a hot water, what they call a hot water geyser in Botswana and a lot of southern Africa. This is essentially a tank, a large water storage tank with an immersion heater that uses a lot. They use a lot of electricity, and they actually cause huge instability to the grid in urban areas across Africa because they draw a lot of power, and people tend to switch them all on at similar sorts of times of the day. So one of the things that SwanaSmartStore can do is reduce that amount of stress on the grid. And it does that in one of two ways. One is by providing, obviously, the solar electricity, which reduces the amount of energy that a household needs to draw from the grid. And the other one is to provide preheated water into the geyser. So if the solar catcher, for instance, maintains a water temperature of somewhere between 30-40 degrees all of the time, what that means is that you need less energy from the grid to power the water geyser. Now I've got here, it's not actually connected to the system, but we have been using it in the tests, an example of a solar water geyser, probably quite familiar to most people, a large tank, a little dial on the front there for setting the temperature, and then water inlet and outlet at the bottom. We've had this hooked up to the solar catcher just to demonstrate and prove the principle that the solar catcher water provides useful preheat into that and reduces the amount of power required from the grid to operate it. And the unit on the back there is more like an instantaneous water heater that you might find above a sink. So we've experimented with how SwanaSmartStore interacts with both of those types of conventional devices, as well as the standalone situation, which is what's set up under the simulator at the moment. Just briefly, just to explain, we obviously have to, in a laboratory situation, measure and monitor pretty much everything we're doing. So most of what you can see in front of you, rather a messy set of wiring, a lot of this is actually the instrumentation. So these here are our current measuring clamps. This is a data logger, which allows us to look at the various different power outputs and currents and voltages. So you can see there that the battery's at 96%. You've got 12.6 volts and 5 amps coming out of that battery, and the solar PV panel is giving us 101 watts. We've got more instrumentation via another data logger to a laptop here that's monitoring what's happening with the power. Now, also some of the functionality that you can see here in these various devices are also the control elements there. So we have relays which switch on and off the immersion heaters and the loads. And in the final system, we will also have the actual digital controller built into all of this as well, which currently isn't active. We're actually doing it manually at the present test.